Okay, what we're going to discuss in section 3.5 is exponential and logarithmic equations. Basically, by that, we're talking about equations which involve exponential and logarithmic forms. Okay, because in general, an equation in general is, in a piece of paper here. See, an equation is an equality like this, and something on the left, something on the right. This is an equation. Okay. If this equation involves logarithm and exponential, then we call it exponential and logarithmic equations. Okay. We have already seen one form of it earlier, but now we're going to look at them in more general form. Okay. In fact, if you go back to section 3.1, let me see if I can find it for you. Section 3.1, 3.1, right? When we discussed properties of exponential function, is 3.1, page 75. You see, we talked about this property. If you have two exponential with the same basis, then exponents would be equal, and if those exponents involve x, the unknown, then we have exponential equations. And then we saw a bunch of them here. These are the special cases where the equation involves the same base on both sides, and even if it does not share the same base on both sides, with a little bit of trick, we can make both sides having the same basis. And then of course with that, when you do that, then you can put the exponents equal and solve for x. Like here, 8, I wrote it as 2 to the power 2, so I rewrote this equation with the same basis like here, and then I put the exponents equal and solve for x. So that's the idea. This is a simple situation when the bases either are equal like these, or they can be converted to situation with equal bases, like these three examples. Okay. So basically that's what we have. Now we have to we're going to look at more general form here, you see, so that the ones we've already seen is a part of this more general situation. Okay, so that's what we have. So basically we have three different kinds of exponential equations. Type 1 is the one that both sides both sides have different bases. So on the left side you have base A, on the right side you have base B, and each one is raised to some functions of x, like a to the power u of x, b to the power v of x. Type 2 is the situation just like type 1, but bases are equal, you see. And type 3, of course, is a situation that you have one exponential involved, and on the other side you don't have an exponential, you just have a number. Okay. So the first thing you do for solving such equation, first you have to figure out which type the given problem is. Then you have to use a particular approach for each type to solve. So let's look at these item A to D that outlines how to find solution of equation of any type 1, 2, or 3. Here we go. First, we rewrite the equation in one of the above forms. So if they readily don't look like these, maybe we have to do a little bit of playing, adding something to both sides, subtracting something to both sides, or divide both sides by something. Then have one single exponential on the left, one on the right, and then we can use whatever the technique is. So that's the first thing you do. You rewrite it in that form. Then, if you get two exponentials, one on the left and one on the right with different bases, then In that case, we apply the natural logarithm of both sides, and then we use properties from previous section to solve for x. I'll show you by one example, just a second. So that's the technique. We apply natural logarithm to both sides, and then we simplify. If you have two exponentials but with the same basis, this is the easiest case because you just set u equal to v, u of x equal to v of x, and solve for x. Or if you have one logarithm on the, one exponential on the left side and nothing on the right side except a number, then you convert this to logarithmic form using the very basic definition of logarithm, which was, maybe I should write it for you. The basic definition, y equal to log of x to base a, is the same thing to say x is equal to b a. Let me rewrite it. Y equal to log of x to base a is the same to say x is equal to a to power y. Okay. So that's we apply here if you have this case. Of course, we can always solve either one of these equations graphically. I'm going to show you probably one case. It's pretty simple actually. Graphical approach to solve is much the easiest one. Okay, so let me do these algebraically, and then maybe I'll do one or two graphically. So here you see this is type 1 because you have one exponential on the right. This type 3. I'm sorry. Type 3. One exponential on the left, and this just a number on the right. You see? So I say type 1. Type 3. Phew, I cannot talk. So to solve, the technique for type 3 is that you convert things to logarithm. So this means, this is to say x minus 1 is equal to this base 3 to power 5. You just replace 5 to up here and bring x down there. Okay. Let me erase this. Just a second. I'm gonna redo this in just a second. Erase it. Okay, so let me see, just a second. Okay, I wrote something meaningless. Let me erase this. Okay, there we go. It's type 3. You see? Type 3. So I have to convert this relationship into logarithmic form. So by definition of logarithm, this simply says x minus 1 is equal to logarithm of 5 to base 3. Okay. Now this guy here, logarithm of 5 to base 3, is just a number. Just leave it like that, and then if you want x, let me get my red pen if I can find it. Then add 1 to both sides. If you do that, these two cancel out. You get x equal to 1 plus log of 5 to base 3. Now if you want to approximate this with your calculator, then let me show you how to do this. I'm going to use my calculator. So I'm going to use the change of base formula. You see, if I rewrite it, if you don't have that feature, so I'm going to just do it the old-fashioned way. So I write this one. Let me erase this thing here. This is equal to plus ln of 5 over ln of 3. Change of base formula. Okay. Change of base formula, CBF. So that's it. That's it. This is your solution. This is the exact solution. But if you put it in your calculator, then if I put all of it in calculator, you see, let me just do it here so you can see. So I have, see, you see it right next to it right there. This is equal to 1. 1 plus, oh, that's wrong place, I'm in the wrong place. 1 plus parentheses ln of 5 divided by ln of 3, then close the whole parentheses. Okay. If you put in there, is about 2.465. So this is approximately about 2.465. Okay, that's your x. This is an exact value. You see, this is exact. This is approximation. Okay, let's look at the next one. Here, this one you have the same basis. This is type 2. Okay, type 2 here, the same basis, and for type 2, since you have the same basis, you just put exponents equal. So here to solve this, you say 3x plus 2 equal to 2x squared. You see, this is what we're going to solve. But this is a quadratic equation. So if I move everything to the right side and make one side 0, so I get 2x squared. Then if you move these two guys to the right side, then you get minus 3x minus 2 equal to 0. This is a quadratic equation. Then I can actually factor this or use quadratic formula. See, quadratic formula. X is equal to minus b. See, a is 2, b is negative 3, and c is negative 2. So if you put all of this in quadratic formula, if you don't remember it, you could go back to your notes and find it for yourself. Minus b minus 3 plus and minus square root of b, which is minus 3 squared minus 4 times a, which is 2 times c, which is minus 2. You've done this before, over 2a, 2 times 2. This is 3 minus times minus is 3 plus and minus. This is 9. Then negative times negative is positive. Get 16 divided by 4. And this is 3 plus or minus the square root of 25 divided by 4. And 3 plus or minus the square root of 25 is 5 over 4. Now again, as the past, if you add them up, if you use plus, you get 8 over 4 is 2. If you use minus, you get 3 minus 5 is minus 2. Minus 2 over 4 is minus 2 over 4, which is minus 1 half. So these are the solutions. Okay. Okay. The next one. We have some more examples here. Let's do another one. This is example B. See, this is type 1 because left side the base is 4, right side the base is 13. to apply the natural log. So I say natural log of 4 to power x plus 1 is equal to natural log of 13 to power 2x minus 7. Then if you use previous section 3.4, let me just find that formula for you. Yeah, see, if you have this property, if you have logarithm of u to power n, this n moves out here, actually becomes a coefficient. You see, so that makes it a lot simpler. So instead of being a power, being an exponent, I can bring it out of the logarithm, put it right in front of it, become a coefficient. That's a pretty interesting formula. Okay, so if you use that formula, this tells you this x plus 1 can come out here and be multiplied by log of 4, and this 2x minus 7 can move back out here, be multiplied by 13, log of 13. Now the point is that if you want exact value, you just have to treat this log of 4 and log of 13 as two numbers. Okay, so but to get approximation solution, what I would do, I just compute what log of 4 is with my calculator. This is natural log, you see. So natural log of 4 is I say 1.4. You see, almost 1.4. So I have x plus 1 times 1.4 is equal to 2x minus 7 times log of 13. What is log of 13? ln of 13 is about 2.56. That's what I said, 2.56. 2.56. You see? Now we can solve this equation by distributing 1.4 x plus 1.4 is equal to 2x times 2.56. How much is that? 2 times 2.56, 2.56 multiplied by 2 is 5.12 x minus 7 times 2.56. So 2.56 times 7. So we get 1792. Okay, so let me explain what I did. First thing I did, took the natural log of both sides because the bases are different. This is type 1. Now that we get this, then this exponent here can come over here, this exponent can come over here. You see, that's what we did by one of those properties from previous section. And then log of 4 by your calculator is about 1.4 and log of 13 is about 2.56. Then you distribute, you multiply in, that's what you get. Then you have to put x's together. I take this guy to the left side and I take this one to the left side. I take this one to the right side and this one to the left side, and I change the sign. So I have this is negative, goes to the right side, becomes positive 1992. This is there must be a period here, the dot right there. So 19.92 plus 1.4 is equal to 5.12x minus 1.4x. Okay, and if I use my calculator, add those two numbers, see 19 point in a minute, I guess 2.5 is 1792. Sorry, what is that? Right there. Wait. This is the typo here. This is 17.92. So this is 17.92 here. The 17.92 plus 1.4. The left side is 19.32 equals to then 5.12 minus 1.4. 5.12 minus 1.4 is 3.72x. Then divide by 3.72 to get x. X is, so divide this by 19.32 divide by 3.72. See, that's what I did. Okay. So if I say push enter, but 5.193 I would say is 5.19 approximately. You see, this is approximation. So if you didn't get it, just play this video as many more times as you need to repeat and see what I've done. Okay. Now the next one, this is neither one of them because of this 3 here. So what I would do first, I divide by 3. So this one becomes 5. This 3 cancels this, so I get 5 to power 2x plus 1 is equal to 17 over 3. And now this is type 3. Since it's type 3, then I convert to logarithm. So 2x plus 1 is equal to logarithm of 17 over 3 to base 5. Then 2x, subtract 1 from both sides, equal to minus 1 plus log of 17 over 3 to base 5, and then you divide everything by 2. So we say x is equal to all of this minus 1 plus log of 17 over 3 to base 5, all of it divided by 2. Now if I put this one in my calculator, see, let me show you one more time. Maybe I didn't move it right enough. Okay, here we go. So let's start over. This is the equation. I divide both sides by 3 first. This 3 goes away and I get this, but this one is type 3 now. So I apply the definition of logarithm to write this in logarithmic form, and this is what we get. And then I just leave this number alone, treat it like a number. I solve for x. So I subtract 1 from both sides, you see, like this. Then this 1 cancels that, and you get this equation. To get x, divide both sides by 2, so you get this. I divide everything by 2. Now I can put this one in my calculator. Let's see. And this is how I put it in my calculator. 1 big parenthesis. So actually what I would do on the paper, I put 1 parenthesis here and 1 parenthesis there. Okay, so I have parentheses, minus 1 plus log of 17 to base 5. Maybe I should do this separately first, because some of you don't have that particular feature, so that makes it a little bit difficult. So let me just do it this way. Let me just continue this way first, for the sake of some people who don't have that feature in their calculator. So this is the same thing as -1 plus, and I have to compute this one separately. Log of is by change of base formula. You see, log of 17 over 3 to base 5 is equal to ln of 17 over 3 divided by ln of 5 by change of base formula. And if I put this one in my calculator, then here we go. See, ln of 17 divided by 3, and all of that divided by ln of 5. So I get about 1.7. I rounded up to 1.1. Okay, so this is approximately 1.1, and that's what this one is. So this is 1.1 right here. You see, so this guy is just this one, and divided by 2, and the rest is easy. So this is equal to, this is going to be -1, 1.1. You just get 0.1 divided by 2. And if you want to see exactly how much that is, say 0.1 divided by 2, you get 0.5, 0.05. Okay, and that's how you do this. Let me do it one more time. First you divide by 3, your equation becomes type 3, then you apply the definition of logarithm to convert it to logarithmic form, and then you go after finding x, so you have to get rid of this 1, so you subtract 1 from both sides. That's what you get. Then divide both sides by 2. That's what you get. And then I use my calculator to compute log of 17 to base 3, 17 over 3 to base 5 by using the change of base formula, or the other feature that I discussed in the section 3.3 actually. So if you all carry all the way, you get 0.05 for this one. Okay, so okay, another example is this one right here. 4 times e to power 2t minus 7 minus 9 equal to 11. In order to solve this, we have to figure out what type it is, but we have to do a little bit of work first. First I add 9 to both sides, then I get this equation right here. Then I divide by 4, I get this one. And this is type 3, and I can apply definition of log, so this becomes 2t minus 7 equal to natural log of 5. And then to solve for x, add 7 to both sides, you get this, and divide by 2, you get this, and then you put it in your calculator, you get 3.4. That's one point. The next one, we have this interesting problem right here. It's type 1 actually, but because the bases are different, but we can convert it to type 2, the same base. We do that by replacing 16 by 4 to power 2. That's what we get. Then because we have 2 back-to-back exponent, then you multiply them 2 times that, you get 1 exponential. Now you have the same bases on both sides, so you put exponents equal, and then this is a very simple intermediate algebra linear equation. You put x's together and y and numbers together by moving 14 to the left side, 1 to the right side. I mean x to the right side and 14 to the left side. That's what you get. So on the left side I get 15, 3x on the right side, so x equal to 5. Okay. I'm not gonna do the next problem here, don't worry about it. So this is another problem, very simple one, is that you have a town with an existing population in the beginning, 14,000, and it's growing at this rate, and we want to know how long it takes for the population to double itself. Okay, so that means A0 is 14,000, K is 0.0095, and we want to know what T should be. T is the time, so that A is equal to A0 equal to 28,000. We start with the exponential growth function, then we replace A0 by 14,000 and A by 28,000 and K 0.0095, and then to solve this for T, this is not this is we have to convert it first to one of the types. So we divide both sides by 14,000. These two cancel out. The left side becomes 2. Now it is type. I guess I forgot to say it. Type. This is type 3. Okay. Then I said it here. I'm sorry, I didn't see it. Type 3. So you convert to logarithm, so that means 0.0095, t equal to log of 2, then log of t is equal to log of 2 divided by 0.0092. If I put that in my calculator, let me see what I get. I get about 72. This is not right. Let me erase this thing here. Find my. Approximately about 73. That means the population of this town would be doubled in 73 years later. Okay. One more before we go to this logarithmic equation is this problem. A mutual fund pays 2.5% compound continuously, so that means P is equal to P0 e to the RT. That's compounding continuously formula, if you don't remember. It's a form of exponential growth. If you decide to invest $25,000 now, how long will it take for the money to reach 41,000? So in other words, A0 is 25,000, rate is 0.025, and you want to know what T is, so that A would be 41,000. Okay. So you put all of this in use formula right here. So I get what is, I should use P0, sorry, right? Doesn't matter, P or A, the letters don't make any difference. You can use any letter for anything you want. So I use P0, and this is P. Initial amount is 25,000, final amount you want it to be 40. Put it in this formula, so you get 41,000 equal to 25,000 e to the 0.025 t. Okay, and to solve this, you divide both sides by 2,500. So if I do that, this becomes 1, so you get 41,000 divided by 25,000. I got 1.64 on the left side, e to the 0.025 t. Now to solve for t, it's a type 3. So put it in exponential form, so you get 2.025 t is equal to ln of 1.64 because it's base e. When you compare to logarithm, you use natural log. So t is equal to divide both sides by 0.25, so you get t equal to ln of 1.64 divided by 0.025. So see how much that is. So ln of divided by 0.025. You see, that's what I log of 1.64 divided by 0.025. If you say enter, I get 19. Because this is a number of years, so just round it up to the next to the nearest integer. So it's going to be 20, almost 20. 20 years. Okay, something like that. So that is it. The next thing, what is the next thing? We're going to talk about the logarithmic equation in just a second. I'm not going to do this problem either for now. Okay, so I'm going to go right to exponential, to logarithmic equations and solve logarithmic equations. Logarithmic equations are sort of the same as exponential. So what we have, logarithmic equation is the one that involves logarithm. Logarithmic equations. So you got to have logarithm in it. There are basically two types of logarithmic equation. One is type 1 and type 2. Type 1 is the one that you have one logarithm on the left, one on the right with the same bases. So in this case, we are not going to discuss situation where you have different bases. Okay, this is simplest case. And you and we are basically polynomial usually. Or you have one logarithm on the left side and no log on the right, just a number. So what we do to solve such equation, first we make sure we have one of these two types, and then if you have type 1, so simply just get rid of log to base a. Just put u equal to v and solve it for x. Cannot be any easier than that. If you have type 2, then put it in exponential. You see, you say u of x equal to a to power c, and then you can solve for it. Okay. Okay. So this, I come back to these remarks in just a minute. Just get to the solutions here. But the only thing you have to do here when you solve logarithmic equations is a little bit different from that of exponential equation, is that basically these are the remark that I'm explaining here. He says first of all we can do it graphically. I'm not going to do anything graphically either. Okay. This remark here basically says that when you solve logarithmic equation, at the end you have to check your answers, because sometimes you solve and get an answer for the unknown, but that answer actually doesn't work. You see, that's possible. We didn't have this situation for exponential equations. I'm not going to talk about the reason why this happens. So, but all I say here is this: when you solve logarithmic equations, at the end, check your answer to see actually it does the job, makes the left side equal to the right side. If it does, it's a good solution. If it doesn't, it's called an extraneous solution. You see, extraneous right here is a solution that you obtain but doesn't work. Okay, extraneous. So let's see, we may run into an example of this sort in just a second. So look at this example. we want to solve for x, and this is type 2. So change to exponential form. So if you do that, that means 3x plus 1. You see, just get rid of this log and then put this 4 to the right side. You see, just if you just put your finger on log and put the space for 2, that's what you get. You see, that's how you get from logarithmic to exponential. Put your hand on the log, your finger, so you don't see it anymore, it's gone, and then move this 4 to the other side. See, so 3x plus 1 is equal this 4 to this power. Now this is a simple equation. 3x plus 1 equal to 16. Subtract 1 from both sides. 3x equal to 15. X equal to 5. Okay, so x equal to 5. If I put it on the left side, I put it check. By check, you put it in this formula or this equation. So you say left side. What is the left side? Log 2 base 4 of 3 times 5 plus 1, and this is log of 16 to base 4, which is 2. Okay, so left side is 2 and right side is 2, and it checked. Okay, let me go over this problem one more quick. This is type 2. See, type 2. Since it's type 2, change to exponential form. This becomes this. Simply by putting your finger on log and say this 3x plus 1 is equal to 4 to this power. Now move this 4 to the other side. Okay, then you get it exponential. And then from there you raise 4 to power 2, you get 16. Subtract 1 from both sides, you get 3x 15, and divide by 3, you get 5. Then check. I put this x equal to 5 here in the original equation. So I look at left side value. So if I put it on the left side, I get 2. And right side is already 2, so 2 is equal to 2. That means it's a good solution. So good. One last page, we are done with this section. This is type 1. So I just put 3x minus 1 equal to x squared plus 1. You see, no more log. So it's a quadratic equation. So you just move everything to the right side and change the sign. X squared plus 1 minus 3x plus 1 equal to 0, and then if you simplify, you get x squared minus 3x plus 2 equal to 0. You either can use quadratic formula or factor. In this case I can factor. X minus 2, x minus 1 equal to 0. You see, this is factorable. If I couldn't factor, I would use quadratic formula, and you know what it is. I already used it once. And then if I put this one equal to 0, we get x equal to 2. Put this one equal to 0, you get x equal to 1. And these are the solution. Now, I have to check to see if things work. You see, if I put for, so I'm going to use red pen for check. We go check. X equal to 1. Left side is equal to. Put x equal to 1, you get log of 3 times 1 minus 1. This is log of 3 times 1 is 3 minus 1 is log of 2 to base 2, of course, to base 3. So left side is log 2 to base 3. If you put it on the right side, is log to base 3 of x squared. X is equal to 1, so it's going to be 1 squared plus 1. 1 squared is 1 plus 1 is 2. You get log 2 to base 3, and check. You see, left side equal to the right side. Similarly, check x equal to 2. I'll let you do that as an exercise. You see what I did? For x equal to 1, I replaced this x by 1. You see, 3 times 1 minus 1. So 3 times 1 is 3, minus 1 is 2, so log of 2 to base 3 is the left side. Right side, I replace this x by 1. So I get log of 1 to power 2 plus 1. 1 to power 2 is 1, plus 1 is 2, so you get log of 2 to base 3, which is the same thing. I got it for the left side. So left side equal to the right side, it checks. So this is good. So this is so this solution is good. Okay, it's good. Check x equal to 2 similarly. Put x equal to 2 on the left side, put x equal to 2 on the right side, and see if you get the same answer. Okay. Okay, 2 more examples very quickly. See, this is neither type. But I guess I may have misspelled neither, N-E-I or N-I-E. I don't know. You just check my spelling of neither. Anyway, neither type. But you can put it in the in one type by using those properties of logarithm. Let me find it again. Right here. You see, if you are adding 2 logarithms with the same base, then you can write it with 1 logarithm and then multiply them instead. You see, log of u plus log of v is actually log of uv. Okay, so that's a good formula. So if you do that, if you use that formula here, then the left side is log to base 2 of x minus 2 times x plus 1 equal to log of 3x minus 5 to base 2. You see, now you have 1 log on the left, 1 on the right, and they have the same bases. So that tells me that I can, this is type 1. So I put x minus 2 times x plus 1 equal to 3x minus 5. This is quadratic. I have to distribute or FOIL this. You see, x times x is x squared, x times 1 is x, 2 times x is minus 2x, minus 2 times 1 is minus 2 equal to 0. See, I multiply it. Now simplify, you get x squared, x minus 2x, you get minus x, then minus 2 equal to 0. You can actually factor this as x minus 2 x plus 1. If you couldn't factor it, use quadratic formula. So if I put this one equal to 0, I get 2. Put this one equal to 0, you get x equal to minus 4. Now I have to check. If I put x equal to minus 1, you see, put check. You see, check. Or x equal to minus 1. You have on the left side, you see, you have log of x plus 1, log of x plus 1. If I put x over there, I get log to base 2 of minus 1 plus 1. This is the left side. And if I put x1 here, negative 1, I get log to base 2 of minus 1 plus minus 1 minus 2 then this is plus, of course, right here. Then the problem is that now if I work this out, I get log of negative 3 base 2 plus log of 0 to base 3, and this is not defined. So x equal to minus 1 is bad or extraneous. This is good actually if you put check it out. I'm not gonna do it, you check that out. And the next one is similar, okay? This is the last example. Next one is similar. The first thing you do, because you have subtraction, you use again this formula here. You see, if you have subtraction between the log, then you write it with log 1 log and you divide them. Okay. Section 3.4 discusses this. So left side I have log of x plus 1, right side I have log of 3x plus 15 divided by x, like that. By property number 3, we divide because we have subtraction between. Okay. Now you have 1 log on the left side, 1 log on the right side, so you put the arguments equal. So x plus 1 is equal to 3x plus 15 over x. Now to solve this, you multiply both sides by x. Like that. Let me start over. Log of x stays the same. Log of 3x plus 15 minus log of x, by using this formula here. One more time. By using this formula, log of u minus log of v is log of u divided by v. By that rule, I can divide these two. This divided by that with 1 log. Now the advantage is that now I have 1 log on the left, 1 log on the right. This is type 1. Because it's type 1, I can just eliminate ln. So this is equal to that. To solve this, there is no log to cause trouble. I multiply both sides by x. This cancels this. So you get x times x plus 1 equal to 3x plus 15. And this is a quadratic equation. You get x squared plus x equal to 3x plus 15. And now I have to move everything to the left side to make one side 0. So 3x, x squared plus x. Both of these two guys go to the left side, change sign. Minus 3x minus 15 equal to 0. And if you do a little bit of simplification here, you get x squared, x minus 3x, you get negative 2x minus 15 equal to 0. You can factor this actually. This is x minus 5 x plus 3 equal to 0. If you couldn't factor it, use quadratic formula. So if I put this one equal to 0, is x equal to 5. Put this one equal to 0, x equal to negative 3. You see, if I put negative 3, you see, if I put negative 3 in there, in this equation, I get log of negative 3 plus 1, I get log of negative 2, and that's not good. Okay? So you don't want to get log of negative number. So this is bad. Extraneous. But this one okay. So check both of them. Okay. First put x equal to minus 3 in this equation. See, if I put x equal to minus 3, you get minus 3 plus 1, it gets minus 2. Log of minus 2 is not defined, so that's why it goes back. But if you put x equal to 5, then you can use your calculator to see you get exactly the same number on both sides. So this is good, and this is bad. And this, thanks God, finishes section 3.5.